Okay, we are now recording, which we were not before. As a result, I'm going to state a few small things to be completely redundant to what I stated before, because I get the impression that maybe a few people don't want to take a look at the video in preparation for the exam. And we're getting an average of around 20 plus views, so people seem to be using the video. In addition, I want to correct one mistake in what I said so that we don't reinforce that point. Cool? All right, so we run the factor analysis. In this case, we're running a factor analysis with 4 factors. We're doing a Varimax rotation that allows us to look at the interactions between factors. That's not a major point with this data set, but it is a practice that I do instead of an orthogonal approach, which forces right angles between each of the factors. So I like to look at those interactions, so it's not critical to this data set. We're only looking at 4 factors to begin with. You will change it. You can look at 2, you look at 3, you look at 4, you look at 5. In fact, PCAs and factor analyses are a little bit of a fishing exercise, but there is actually a really good logic behind the decisions you make. There are 2 points of logic. One is, our latent variables, these factors, need to do a better job explaining the data than any one variable by itself. So if there's one variable by itself who does a complete job explaining a factor, we don't need that factor. It's worthless. We just use the original data. We only use factors when they do a better job explaining the data. And there's a few ways to think about when a factor does a better job or not. Looking at the output, which is right here, and I grabbed that and I brought it over into the Excel file to make it just a little bit easier for us to look at. The first thing you can notice is whether your eigenvalues, the SS loadings, are those greater than 1? Eigen, E-I-G-E-N, V-A-L-U-E, eigenvalue. Sure, E-I-G-E-N, G-E-N, V-A-L-U-E. The take home from the eigenvalue, not how it's calculated, but the take home from the eigenvalue is it describes the overall contribution of that factor. And therefore, if it is greater than 1, it does a better job explaining the data than any one of the variables by itself. Our first eigenvalue is 4.16 for the first factor. That factor, MR1, does a better job explaining the data than any one of those 17 measurements I took on the wasps. We want that factor. It is better for us than the tibia length, than the gaster length, than the thorax length, than any of them. It's doing us a good job. The first 2 rows describing variation describe variation relative to all the variation of data. That's why I said something wrong. So if you take all the data together, this tells us that the first factor explains 26% of that overall variation. It's why the cumulative variation does not add up to 1. There are ultimately 17 factors. Not all of them are important. In fact, when we get out to the last few factors, they do nothing. They're terrible. We don't want them. We really are trying to reduce data, and we're trying to describe underlying patterns. The bottom 2 rows describe the amount of variation of the measured factors. So again, I said that statement wrong the first time. The first 2 rows describe the variation relative to all of the potential factors. And in these 4 factors, they explain 66% of the variation. Factor 1 plus factor 2 plus factor 3 plus factor 4. Together, they explain 2/3 of the data, which is dramatically better than any one variable by itself, which only explains roughly 6% of the data. The second variable, factor 4, which obviously should be factor 2. I don't know why it's factor 4, but it is. Lucas, is that a useful factor for us? Is the eigenvalue greater than 1? Does it do a better job explaining the data than any variable by itself? Yeah. In fact, one of the things that's nice about this is that the use of these eigenvalues gives you a very clear and very justifiable decision. If the eigenvalue is clearly greater than 1, use the factor. It's doing a better job explaining the overall pattern. Again, we don't know what those mean yet. We'll go into the biology in a second. We're just going back through that idea. What about the next factor? MR2. Clarita, is this doing us a good job? Yeah, it is. That eigenvalue is 2.49. That is greater than 1. This factor is doing a better job explaining the data than any one variable by itself. And if we look at the fourth factor, that is also doing a good job. Maybe not as good, but still a good job. The eigenvalue is 1.34. That is greater than 1. So that fourth factor also does a better job explaining the data than any one variable by itself. The first factor explains 26% of the variation in the data. The second one explains 17% of the variation in the data, then 16, then 8% of the variation in the data. So each of these are doing a pretty decent job explaining the information, with maybe the fourth factor not giving us much. So that's a statistical interpretation about whether these are useful factors or not. The second thing you want to pay attention to is the biology. If the biology also agrees with decision, then good. And that actually gets to be a pretty simple thing. If only one variable loads on a factor, then ignore the factor. And I'll show you what that means now. Questions with this? Paul? You keep adding factors. Once you get below 1, you rerun the model back with one less factor. Yeah, you get rid of it. Doesn't do you any good. It's totally worthless. So far, so good? Okay. Loadings. These are individual loadings. They describe how the variation in each one of our measured variables varies with a factor. This time, we use kind of an arbitrary threshold. We pay attention to loadings that are either 0.5 and greater or negative 0.5 and less. And what I do with these is I put them in Excel. And I just start by highlighting things that are .5 and greater or negative 0.5 and less. This is where sort comes in handy, because it's going to try to sort based on that first factor, give you some basic information. Loadings are very much like a correlation coefficient. They describe how important the measured variable's variation is to explain that factor. So in this case, we have 8 different measurements that all load positively on the first factor. So an increase in LSM is associated with a larger SSM, which is associated with a larger G1PW and a larger G1H. A small measurement in G2L is associated with a small measurement in HH, associated with a small measurement in tibia, so that a large measure in any one of these is associated with a large measurement in all of them. A small measurement in any one of these is associated with a small measurement in all of them. So far, so good. Values in between 0.5 and negative 0.5, they don't have a strong relationship to the factor. So we don't pay attention to them in terms of that factor. This, and we start to define the name for the latent variable. And what's a good name for variables that all have a morphological character that associates positively with each other? So small size in one means a small size in all of them. A large size in one means a large size in all of them. What's a good name for that type of variable? Yeah, what would we call it? Size. So it is a latent variable, but really what it is it's telling us size. And this is when I start to rename things. I look at the relationship between the loadings and I name them based on that relationship. This is describing a positive relationship between these morphological traits, which means that we're getting a description of size. Larger animals will have larger values for each of these. Smaller animals will have smaller values for each of these. Make sense? Okay. So we do the next thing going down. Again, we're looking for variables that are either greater than 0.5 or less than negative 0.5. When we go down, these two are greater. This one is greater. And there we go. Here, we have sort of a positive relationship between measurements of head and the measurements of gaster length. So this is describing an overall body size. It's describing a positive relationship between the head and the abdomen. What's that? Oh, this is the maximum inter-eye distance. This is the first gastral length. MSH, let's take a quick peek. MSH is the metasomal height. So it's describing the distance between the eyes, measurements of the gaster, and mesostotum. So it's kind of another body size. Questions? Yep. Yep. Questions? Jackie? Love it. Yep. I go here into the output. Let's copy and paste it. Nope. I paste. Then I go over to data. And I go to data, text to columns. And I go through this until I get the columns that I like. And next, and then hit finish. The next thing I do is I select it all. I go to view, and I zoom to selection. Would you all like me to do that again? So in R, I select the data I'm interested in. I copy it. I go to my Excel file, not my CSV. I go to my Excel file. I paste it. It puts everything in one column. And you can see that up here. We have space, item, MR1, MR4, MR2, MR3, H2, U2, commonalities. I go to Data tab, and I do text to columns. That's going to bring up a new window. And if you have some character that you're using to define columns, like a comma, you can do that. But typically, Excel does a good job trying to find the columns. I can see where Excel is trying to find the columns by, when I hit next, it put in these black bars. If those look like good places to have a column, I keep them. If they don't, I double click it, I get rid of it. I want the column there, so I'm going to put that back. And then I hit finish. That will then separate out those pieces of information into individual columns by themselves. And then highlight all the stuff to make this bigger. I got to zoom to selection. That makes everything large for me. I'm highlighting everything greater than 0.5 or less than 0 or negative 0.5. One thing we can do if we want to, we'd use sort. And we can highlight our values that way. But I'll go back to the way we got the data from R. This is where we were. Questions about to this point? Yes, sir. Everything on column A are Watt's body parts. Yes, sir. Yep. And when we look at MR2, we're kind of getting another measurement of size. So they're both kind of giving us size. This is giving us size, a little bit based on gaster, a little bit based on the thorax, a little bit based on leg length. This is giving us size, a little bit based on head, a little bit based on gaster. They're both giving us a little measure of size. I think I call this first one size. That's our F1. Then I'm calling the second one head and abdomen. F2. So far, so good? You know, it really doesn't matter. And I like to order them. 1 has the largest eigenvalue, 2 has the second largest, 3 has the second largest. I cannot tell you why R put it as MR4. And I definitely wouldn't keep it as MR4. I would convert it to second factor. Max? I don't understand the question. I'm so sorry. Include it. Yeah, 0.5 and above, negative 0.5 and below. Both of those. So when we go to the next factor, we scroll down. We're not going to use LSM. We're going to keep going down. Now we get to a few. We have those. And we have this, which is kind of describing the positive relationship between I and SW. Oh, this thorax character, which is a plate along the back of the animal. So we could say I and thorax. F3. Questions? All right. Something interesting that we're going to use to make a decision in the last factor. And that is how many variables load onto that last factor. There's 1. So this factor is not useful because this factor is describing the variation in one trait. And since it's describing the variation in one trait, we might as well just use that trait. There's no point of going through this complexity if what we measured actually does the same job. So even though the eigenvalue for final factor is greater than 1, because there's only one influential variable, we don't want to use it. Does that make sense? Great. So we have 4 factors. One of them's not usable. At this point, what we do is we test for 3 factors and then 2 factors until we get a model that does a better job explaining all the data than the original measured variables. Probably just a single variable by itself, and therefore also not useful. Now, when you're doing this for real, I would probably do it. So I would do 5, I'd probably do 6 until I get an eigenvalue that's less than 1. But anytime that I get a single factor by itself, which is explained by one variable, there's no point in that. So I'm going to start reducing my models and using small number of factors. It would then change its relationships. Yep. Yep. Questions? All right, so let me do one thing to put your mind at ease before I task you back to good, fun, hard stuff. You are not going to have to do this for the open test. For the open book test? Nah. Yeah. No. No, what it means is you're not going to have to actually run it, but I'll be happy to give you data and you can make decisions on it. Does that make sense? Yeah. So you're not going to run this independently, but I will give you results or I'll give you inputs and you sort of have to process those and make sense of those. So as part of the study, I would take a look at the video. I can give a practice data set. If you want to play with the data set, please do, but you will not have to run it. That being said, we're going to continue working on it. Questions? All right. So what I want you to do, I want you to change the number of factors to 2, to 3, to 5, to 6, probably all 4 of them, until we settle on the appropriate number of factors for these data. In all cases, we should have eigenvalues that are greater than 1. That's an appropriate number. And we should have no one factor by itself that only explains one variable. Every factor should be explained by more than one variable. Each time you do this, do the same printout, take the data, put it into Excel, and then start to take a look at it. I would separate them out by taking out both results, the results of the factors with their eigenvalues and their variation, and then a result of the variables and their loadings. I can't hear you. Yeah. I don't know. It's a little annoying. I like The Simpsons. That's funny.
Going down or going up,
Oh,
Any correlation?
we're going to do it just because it's class.
Oh.
And real, as soon as you get that fourth factor with just one variable, you're not going to any higher.
Whenever I graph mine, the first one with the 8% correlation or whatever.
There's something weird in your data though, and I'm not sure what's going on.
I don't know.
Has anyone else getting different numbers than what I'm showing you up on the screen? You're getting different numbers? Well, that is way different, but I'll come take a look at yours as well. There's something in the data. Could it be that you're using millipedes? No, I mean, you can't be in the right sheet, are you? Okay, thank you. Thank you. Thank you.
Sorry.
Open it. Oh, yeah, you're missing a variable. I just found it. Don't know which one you're missing, but it should be 17 variables. Yeah, 16.
I think that's because I deleted this one and I haven't ran it yet.
Run D, but you got to go back and run DF. Stop. Okay, we got 16 again. So what are we? Oh, did I put in log ovary? And I'll be there in 2 seconds. .5 and larger or negative 0.5 and smaller? Who 0.5?
This is your code. I have the same variables you do, right? But Max does not. Max does not have log of ovary, but he has the same numbers you have, and I'm getting different numbers than you do.
You are. I'll keep thinking. I'll keep thinking.
Oh, mine wasn't like very different, but it was just like slightly different.
Oh, because you have 5 factors in this
That
one.
was like the original one.
Okay. Now you have 3. That's good. Scroll up. Let's see. Keep going until you get 4. So you have 5 there. That's good. Keep going. That's smart. Huh. Okay, let's scroll up on this one. You're good. We're the same. Yep. Well, there's ever so slight differences.
It's like a couple.
It's not a lot of difference, but it's a slight difference. Mind if I scroll up there? You have an extra variable, log ovary. Don't worry about it. You got the same basic idea, but that's what's going on here. I have ovary removed. You have it in. That's it.
You wouldn't want to go above.
Is that 3?
What was the next step after this?
Try 2. Try 2. Try 5. Try 6. See if it does a better job explaining.
How do you know if it does a better job?
Some of the rules of thumb we've talked about it, and then I'll add in a few more once we get some more going.
Okay. So is it just that like most of these are explained by it?
Ideally, in most situations, you want a variable to only load on a single factor.
Okay.
You want it to ideally fit just one factor.
Okay.
It won't always in every situation. And morphology, it tends not to because that first variable size tends to overwhelm everything else.
Okay. So I'm just curious. What you're asking us to do is to change the number of those factors, correct?
Yep.
Okay. So when we run all of that, let's say like the last one that we ran that is on cancel is factor 2, and like the lower the factor, the lower the factor, it's like better it is, the more useful. What am I trying to understand from this? What am I trying to gain from this?
First thing you're trying to do is, hey, Heather, can you let Maria back into the class? We're trying to do 2 things. One thing we're trying to do right now is identify variables, latent variables that do a better job than a measured variable. So we're really trying to do two things. We're trying to find latent variables that are explained by more than one measured variable. And two, we're trying to make sure that all of our measured variables are explained by at least one factor. That part I haven't told you yet. That part I wanted us to do a little bit more.
Okay.
Then we can do two things. One, we can actually literally describe it. And there's a lot of work which just describes the relationship between the measured variables in these latent variables. You know, like the relationship between SAT, SATs, IQs, GPAs, and career life earnings. That could all be possibly explained through a factor. Maybe some of them are interrelated, like the ones that are based on just sort of tests, tend to be highly related, but they actually don't do a very good job explaining other characteristics. So you just describe those patterns. That's one. The second is what we'll get to at the end of the class, which is about taking these variables, putting them back into our original data sheet, and then actually use them to address the questions Chloe talked about.
So then for each of these new, for each of these lines where I'm running different number of factors, is this the line that I'm supposed to look at?
That tells you whether you should pay attention to it as a factor.
I had it both. Was it not actually done?
So does this factor do anything? So right off the bat, we know that this is not the right model because our smallest factor is doing nothing. It's no good. So this tells us statistically, should we pay attention to something? And then we start to use this to tell us biologically, should we pay attention to something?
Why is one so high?
What's that?
Why is one so high?
Oh, because it's just based saying, force the relationship between everything you measure. Yeah.
But that doesn't mean that it would be the best choice.
It may not be because if we look here, we have a number of variables that don't do anything. SC and min IEX don't do anything. So they're just left by themselves. So one does a very good job. We wouldn't want to use that because we lose two variables.
Okay. Looking at the loadings and the SE number.
Yes. Question?
I just can't wait until you tell us what the heck this means.
You let Maria back in the class?
Yes,
She's got bumped again.
I know. Oh, again. My computer's like, it's turning off.
All right. So we run this. For all practical purposes, I told you to go to 5, 6, some people went to 7 and 8. As soon as you get a situation of one of two things occurring, your eigenvalue for a factor is less than 1, or you have a factor that's only explained by one variable, you've kind of hit it up a threshold, start going the other direction. So since our first example, 4, had a factor where there was only one variable that loaded onto that fourth factor, we can start going smaller. If you did 5 and 6, it's still a very good exercise just so you can start to see those types of relationships. But in terms of being practical, we can now start to reduce. 4 doesn't do us any good. Why doesn't 4 factors do us any good? Perfect. The reason we're not going to use 4 is because that last factor, in the case where we had 4 factors, was explained by one variable. And for that, we should just use the variable. Okay. So do you want to start with 1, 2, or 3? 2.
Like because like if you like read like I guess you're fishing like right like we kind of are.
You are fishing.
I guess it is more than but
This is part of the approach.
so let's like why wouldn't you because like I went to 6 right so I did like 5, 6, 7.
Yep.
So like 5 doesn't work because there's factors that are only described by one variable and 7 doesn't work because your E is called eigenvalue.
Eigenvalue. Yeah.
Eigenvalue is less than one of the
Yep.
factors. But 6 like is
It kind of gives you good information. The second thing you do is you think about the biology. So this really is an approach where we're thinking about both stats and biology at the exact same time. And this is an approach where you use it for one of two things. Well, actually use it really for both. One of the things you use it for, what we're looking at right now, and that is to understand latent variables. So size measurement, intelligence measurement, and allometry, which you can't get until you sort of look at those relationships. If the biologically makes sense describing particular allometry, then you continue describing it. That is part of your decision. So it's not just stats. In this case, we're not really paying attention to p-values at all. The generate one, don't really care. Not part of what we're doing. But when you write it up, how many people have done, maybe I can explain this slightly different way. How many people have done phylogenetics? You make trees. Is there a right tree? No. And when you write up phylogenetic papers or you read phylogenetic papers, we're talking about evolutionary histories. Do they talk about one tree? No, they generally talk about a tree, explain the assumptions, explain the limitations, talk about another tree, explain the assumptions, explain the limitations. And then part of the paper is arguing out, this is the most appropriate tree given these conditions, but the decision is not just a statistical decision. A statistical decision, biological decision, sometimes you might be using parsimony, sometimes you might not be, sometimes you might be using casuistics, sometimes you're just leaking little phonetics in there, even though no one ever admits that, but that's a lie, they do. You're sort of arguing up using both the math and the biology to make a decision on. Factor analyses are really kind of the same. We're using a little combination of both the biology and the stats to make an overall decision. Make sense? Good question. Paul, and then Kyle, I'll come back to you. Paul? You want to pay attention to it. Yep. Statistically, if the eigenvalue is greater than 1, pay attention. Statistically, if more than one variable loads onto that factor, pay attention. Those are statistical determinations. Biologically, if it actually does what you want it to do. Biologically, if it actually makes sense for what you're trying to understand. Those are also part of the considerations. Two or more, and they provide value. That last part, you got to know the biology before you could say that. So that is not something I will be grading you on, whether you identify something as having biological value or not. So it's kind of like, when I'm going to go back to phylogenetics. When you use some phonetic approach, it's because you understand the biology. So if you get a tree that makes perfect statistical sense, but it's just stupid, you don't describe it. Just doesn't make any sense at all. Yeah, you'd be like, fishing is the right word overall. Elizabeth? You could, though I like your question, it kind of devolved after a little bit of time, but you could. Yeah. And Kyle, did you get your question answered? Okay. Oh, that's when you're using morphology. Allometry is an interesting thing in morphometric studies. Now, don't worry about allometry. Latent variables is what you care about. Oh, in this case? Yeah, it's 3 is what I'd be using. As soon as I got 4, when you got 1 by itself, I'm done. I'm not going down until I find something. Sure. And then what do you go through when you submit a paper? Yeah, they're going to say that's crap. No. Oh yeah, they'll be part of your, both part of your methods and your results. How you just make those decisions. Again, I think right now for most people, if you think phylogenetics as the best model for sort of thinking through this, how we describe phylogenies, how we write up phylogenies is very similar to how you deal with this. What? Yeah, okay, so let's do 3. We're gonna run 3. Okay, so Jackie, are these 3 factors, are they appropriate statistically? No, just give me based on the eigenvalues. So sorry, based on the eigenvalues, are we okay with them statistically? Absolutely. Each one of these is greater than 1, so we're fine with it statistically. The first one explains 22% of the variation, 21%, 19%. Together, the 3 of them explain 62%, which is not as good as 4 factors. That's not surprising. You got more information, 4 factors. That's going to do a better job, but that 4th factor doesn't do us any good. Sam? True, but in this case, we wouldn't use it because it was only with 1 measured variable. Like we're done with that 4th because of 1 measured variable. Okay, now there's another thing that we want to pay attention to. I know, you're welcome. Ideally, we want all of our measured variables to load in at least 1 factor. And ideally, we want them to only load on 1 factor. So we want them to be associated with 1 thing, ideally, and we definitely want them to be part of something. Otherwise, they're not doing us anything. We're ignoring them. So for this first one, I called you earlier, right? Okay, I just didn't delete it. Ariana, do we have loadings on that first factor that kind of make biological sense? MR1. Positive, 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 positive. They're all kind of going the same direction. That kind of makes sense. Emily, what about the second factor, MR3? Yeah. Yep, we go down, we got a positive here. So that means head height is positive for both of them. Ideally, we don't want that. We want it to be on 1, but it's there. And then we go down and we definitely have some additional ones that are only positive on that second factor. GH, G1H, G1PW, SSM, LSM, and tibia. Yep, that looks pretty good. Olivia, what about that third factor? Yeah, we're doing pretty well. We got the last 4. We got the last 4 values. We got M as W, min, inner I, MSL, and SC. So they all kind of make sense. Yep. Yep. That's a kind of a problem. So that's where we kind of have to make decisions. So now we have 1 variable that's out by itself that is not being explained by anything. That you can say. This is where you sort of make decisions and you make arguments for this. So ideally, we want each of the measured variables to load on at least 1 factor. Ideally, we want the factors not, each of the measured variables not to load on more than 1 factor. And we definitely do not want one variable as the only variable to load on a factor. Because then it just doesn't give you as clear of a story to explain what that variable is doing and what it's contributing to. But that's why I'm also saying ideally. That's not a black and white rule. Yep. Depends on what you're trying to describe. Yes. Heather? 0.5 is a borderline. And by the way, on the 0.5 and above, negative 0.5 and below, that's a little arbitrary. It's a good rule of thumb. You know, after the variation, its variable is explained within its factor. It's a good rule of thumb, but don't get me wrong, that is kind of an arbitrary delineation. In fact, it's a little more arbitrary than even a p-value of 0.05. It is a rule of thumb, but it's a rule of thumb. All right? That's what we get when we do 3. Yeah. Oh, these are other aspects of the calculation. We're not going to worry about this. Commonalities, overall, yeah. A negative correlation between the variable and that factor. So as an example, when this increases, this decreases for that animal. Oh, God, yeah, absolutely. We just don't have that in this case. And you don't tend to get that with morphometric data. You definitely get that with behavioral data. And you kind of think about an animal that avoids novelty is going to be very different than an animal that is seeking out new food items. Those are going to have opposite patterns. Hello? Yeah, you have more, you're trying to do more than the data allows you to do because there's not enough data. Cool? Good. All right. So we do 2. We got our next setup. Victoria, are we cool with both of these factors? Statistically, according to the eigenvalues. Oh, no, true. We'll get to that in a second. I was just asking, according to the eigenvalues, are we good with both of these factors? So statistically, are these factors a good representation? Great. That second part is what you were going for, but I'm gonna let someone else. Actually, go ahead, you're there. So what are our problems? No, that's okay. I mean, it's looking pretty nice. One, LSM is on 2 values, but all of our variables are loading on at least one factor. And we have one that is clearly, for a morphometric issue, an indicator of size. And that has a positive relationship between almost all of the variables, where then we have a secondary thing associated with that segment on the back of the animal and the inter-eye distance. And SC is this little cell in a wing. So it's kind of a weird combination. Something about having thin eyes with a plate in the back, and then this very thin little cell on its wing. Max? Yep. Yes, that's exactly what it is. In fact, the way that it is described, it's an n-dimensional linear regression. So where linear regression is 2 variables, this is n number of variables. Let's just do the last one. One factor. And Sam, start me off statistically. We're over 1. 50% of the variation is explained by that first factor. And what is the relationship with that first factor? Size. Everything loads onto it except for the bottom two variables. So now you make a choice. And George, you get the privilege. Should we be using 4, 3, 2, or 1? Why? Yep. I'll give you one more reason why 3 makes sense in this case, but it's based on how I described the original biology and the questions that we were exploring. And that is, we thought there were going to be allometries. So while that first factor gives us information about size, we were still testing whether there were genetic influences that were affecting reproductive status, and if there were allometries associated with them. So for that very reason, we wanted to have that information still within the data to see if it associated with the different animals and their different strategies. So again, statistics and biology kind of come into play to sort of make a decision on what you are doing and what you're using. Chloe? Oh yeah, when we came into this system, we thought reproductive status was determined by genetic variation. That there were alleles associated with females who became reproductive and different allelic variation for those females that became, we'll call them workers. And that's similar to other social insects. There were going to be allometries that would be indicators of those differences. Like a queen bee could be bigger, but she also has a different body design than a worker bee. So we wanted to look for those overall allometries between characters to see if this pattern was emerging within these animals. We wanted those 2 additional variables to look at that. We dropped the 4 because it's one variable by itself being influenced by a single factor, but then the other 3, we want to take a look at factor 2 and factor 3. There are ways of describing the relationship between different measurements. So there are allometries. You just want to look at size. You're doing a social science experiment. All you want to do is look at the degree of aggression. You're doing a social science experiment. All you want to do is look at novelty seeking. How willing an individual is to engage a different idea. And that's all you care about. And you're looking at all these different indicators to get a measure of that. In that case, I would use one factor. And then for those variables that don't contribute, that would actually be part of the results. These are not giving us good indicators of this. So they're not really useful tools. So it's actually allowing us to discriminate out on valuable measured data, as well as to get that overall composite. Yeah, and you do. Yep. That's part of what you do. You're justifying why you're making different decisions. You don't see this much, and Max, I'll come to you in 1/2 second. You don't see this much in Biostats 1, where everything is sort of a clear-cut decision. But as you do more statistics, you get into changing the stats, modifying the tools, and justifying how and why you make the different decisions you do. And it's not black and white. You are doing it exactly like you would a methodology, In your research, in the methodology of your research, you are making decisions. There's no one right way for doing it. And part of making those decisions is just finding out why you do all those things. You end up doing the same thing statistically. This is the first example we've really had of that type of approach. Max? Yep. This is one of the reasons why this is one of the only places where I would do transformations for exactly that point, to get them on the same same structural, same sort of dimensional orientations, because you can't do this where one thing is exponential and another thing is linear. You need to have all the data basically function in linear space. So you can take log of the data, you can take a square root of the data, and try to create a linear structure to it. Or you can't use it. Yeah, yep. Yeah, an assumption. Yeah. Questions? That's all right. I don't get to give you joy every day, just most days. Go ahead. No, okay, so what you don't get with this approach, except for the statistical parts, like the eigenvalues being greater than 1, is you don't have clear set rules. You got to make choices. And there should be logic to those choices. Some of them are just, they make sense. A loading above 0.5 and a loading less than negative 0.5 makes sense. That variable is associated with the factor, but then why not 0.3? Or why not make the threshold 0.6? That doesn't make as much sense. So the idea behind it is half of the variation is contributing to that factor. That's the logic why it's 0.5 and negative 0.5. It's logical, but it is a little bit arbitrary. A lot of what we do in stats seems like it has these fixed rules, so it really doesn't. It's why you have to be very clear why you're doing, what you're doing, how you're doing. And then I'm going to come back to you because I just want to show you why we use it and what it does for us. Yeah. I'm so sorry. You lost me somewhere, and I think it's me. Try again. Mhm. You want to reduce the variation relative to the best fit line. Yeah, this is where it becomes difficult. You can't really graph this stuff out, and you can kind of see why. It's more than 3 dimensions. You can't graph that out. So what we do end up graphing when you graph, which is very rare, by the way, is you generally graph a regression of factor 1 and factor 2, a regression of factor 3 and factor 4, sometimes a regression of factor 2 and factor 3, but a lot of times it's not done. And then you're sort of describing those relationships there. But that's why I get this number with a Varimax, because that actually gives me that information about their relationship, whether it's positive or negative, whether they're closely aligned, distantly aligned, stuff like that. All right, so I want to show you why we go through this torture. It's not just to reduce the number of variables, but, and we'll do this on Thursday. One of the things we could do is, and don't type it down, this is just an introduction, we'll go on Thursday, is we can regress the loadings back to each individual animal's measurement to get a variable that describes that animal's measurement for each of those factors. This will give us a variable for size, and it will give us a variable for each of the allometries in this case. And then we could do what Chloe started at the beginning of class saying. We could do something like a ANOVA or a two-way test to look at how maybe reproductive investment or season is associated with the size of the animal. Whether reproductive animals have a certain allometry that is higher or lower than non-reproductive animals. Whether animals in the spring tend to be larger than those in the summer, which you cannot do without actually having a variable. And you can't actually have a variable with any one number by itself. So we do this amalgamation to get this data reduction, and then we regress the loadings back in to give us a measurement for a latent variable for each of our animals. And then we could do traditional statistics with it to look at the overall question that we had initially, which was, is there an alternative strategy that explains these animals, and therefore there's genetic differences behind their reproductive investment? We'll do that on Thursday. The other half of what we'll do on Thursday are statistical traps, and then the open book test loads as soon as class ends on Thursday. If you have any questions, stick around. If you don't, have a good day. If you prefer not to think about principal components for an entire 2 days, enjoy those.